really happy to have physically Professor Cengiz Pehlevan from Harvard University. Dr. Pehlevan is an assistant professor of applied mathematics in Harvard University, and he's also associate faculty member in the Cengiz Institute. His research mainly concentrates on the mathematical theory of artificial and biological learning. And he's a recipient of several awards, including Sloan Research Fellowship in Neuroscience and NSF Career Award and Google Faculty Research Award. Dr. Pehlevan was previously in Flatiron Institute Center for Computational Biology and generally a research campus. And he was also a Schwartz Fellow at Harvard University. He has a PhD in physics from Brown University. So we are really happy to have you.
Thank you. Thank you very much. And thanks for inviting me twice this year. It's much nicer to be here in person. So I already gave you a talk about an hour. It's the way I feel it. The previous talk was more of an overview talk. So today I'll try to do a bit more technical subject. And what I'm going to talk about is basically this idea of neural scaling laws. Why is this an important problem?
Ben de şey yapabilirim. Yani
Next one.
da oynamıyorum. Anladım. Evet. Bir üretsek aslında bir üretsek
Sonra demiyorum.
It's extended. Okay, sorry about this.
This fails again to find out solution. All right, so well, I guess I don't have to repeat this, but we live in the world era of AI. Artificial intelligence is basically taking an effect on all our lives and all our, science and technology and daily lives. We can ask, why is this happening? Why now, right? What is the main driver behind all these technological advances? And it's this dominant AI paradigm of scaling. By scaling, I mean just throw more resources at the machine learning models, and somehow they get better. Now, again, in my talk, the previous time I had the slide, but let's just go over this. So in the modern era, this observation that giving more resources to the AI models gets you better performance, basically was observed in 2 or 3 key papers. So this is the second one that I'm taking this figure from, a paper by Jared Kaplan and colleagues, titled Scaling Laws for Neural Language Models. And this is a famous figure from that plot, from that paper. Let's just go through this in detail so we're on the same page. Let's start from the middle panel here. On the y-axis here, what we're looking at is the performance of a model. Lower means better. Test loss low is good. On the x-axis is data set size. A token is basically like a word. So the more training data that you provide with these models, the better performance you get. So that's not surprising, right? So, I mean, in general, we expect more data to give us better performance. Maybe a surprising aspect of this is if you put this in a log-log plot, you get a line, meaning that there's a power law relationship. There's a particular exponent here, which looks weird, but but that's maybe a relation. The second plot to look at is the one on the right. So this is perhaps more surprising. Right? So now this says if I keep increasing the parameters, making models larger and larger while keeping the data set size fixed, models basically keep behaving better and better and better. Now, if you're coming at discipline like statistics or physics, or you're into mathematical modeling of some sort, right? So this is surprising finding because our intuition before this was that there's a sweet spot of parameters. You don't want your models to be too explicit, otherwise they would overfit noise and they would be behaving bad. But it sounds like in the modern era this doesn't happen. And I could give a whole other talk about why this may or may not be happening, which I haven't brought, but that's the observation. And the third plot to look at is this one over here, which is a combination of these two plots, but plotted in a different scale. So on the x-axis is compute. What that means is how much computational power that you spend. So each of these lines here, so compute should increase with parameters you have because it takes more computational effort to calculate its output or take gradients. So each of these lines here are basically a model of a particular size, and you're adding more and more data, you're training more and more, and that's what each of these lines are. So if you look at this frontier curve here, for example, if I were to commit to a particular compute budget, okay, and basically chose the best performing model in that family of models. So this dashed line here gives me a compute optimal frontier, and that particular frontier also has a power law behavior. It also gives me the finding that as I spend more and more compute, my models are going to get better and better and better. Okay, so this particular observation was very influential because it suddenly gave people an idea, right? What we need to do is just spend more money, build bigger models. That's going to give us better and better performance. And that basically ended up in the following idea, like predictable performance gains from scaling have led researchers to train larger networks. So here is a plot from GPT-4 technical report. So this is available in archive, so you can just take a look at this. Okay. Here's what it shows. So on the y-axis is again a bunch some performance metric. Low is better. And on the x-axis is again compute, normalized to 1 GPT-4 units. So they don't tell us how much compute they spend. So they don't label their axes, but that's what that is. So these gray dots over here is a bunch of models that they had trained. And then they fitted this power law to it. And they made a prediction that if they trained up to that scale, GPT-4 model would perform this good. And they trained the model and they got the prediction right. Okay. So I just want you to notice one idea here. So this is, oops. Okay, sorry about that. Something wrong. Okay. So this is 1 unit of compute. That's 100 microns of compute. So the idea, the difference is 4 orders of magnitude. So they were able to extrapolate 4 orders of compute magnitude and basically get a great prediction. Right? So again, if there's a physicist in the room, that's almost impossible. But in this business, it happens. I may not have the quote, but if you again read the GPT-4 technical report, there's another paragraph there. What they say is basically this doesn't come out of the box. It's a serious engineering effort to get models behave this way, so you can make predictions of this. Okay? Good. So if you're wondering what this number is, basically there's an estimate there. It's about 2 times 10 to the 25 flops. I don't know if it's correct or not, but that's what people think about. Okay, good. So what about these power laws? What do we know about them? There's a later study by Jordan Hoffman and colleagues. These folks were, I believe, Google DeepMind at the moment. The paper goes under the name scaling laws. It refers to a particular model that they have trained. So what they've done is basically they've come up with a curve fitting exercise. They collected all the models that they've trained, and they noticed that the loss, okay, is well described by this functional form. It's an empirical fit. N here is the number of parameters. D is the number of data pointed at given these models. E, N, C, D, C are some constants. Alpha and alpha here are again some constants. parameters. So if you fit all these parameters, basically you get, these scaling exponents, 0.34. There's a later paper that claims that a better procedure would give you these exponents, and so on and so forth. Okay, so this talk is going to be about where do these exponents come from. We're going to talk about that a little bit. Actually, the first half of this talk is going to be about that. But I just want to give you a side information about this. So how would you use a functional form like this? Now, suppose you have some money budget. So someone gave you $100 million to train these models. So that basically maps to a certain number of compute time. Okay. So your goal is basically, after you've done this fitting, to optimize for the optimal model size and how much data that I'm going to use to train this model with. Subject to that constraint over here. Now there's a back of the envelope calculation that's going to tell you that the amount of flops is 6 times the number of parameters times data. Okay, so you can put that constraint over here in that this functional form, and you're going to get basically a scaling relationship like this. If you're increasing your flops, you should be scaling your model size with the power 0.5, and the number of data that you give your models to the power of 0.1 to the power of 0.5. So they grow similarly. So basically, when you're training these models, you should, to get optimal performance out of them, you have to scale your model size and data together. So this particular heuristic is basically standard practice nowadays. There's even a name for this, Cengiz rule of thumb. It says basically you should use about 20 tokens per parameter if you want to get like a good performance compute optimal training. If you don't have the budget to do the search, you can just go with this and you're going to get close to training. These are all good ideas. Okay, good. So, but however, I mean, these are all great, but I mean, there isn't the first principles mathematical understanding of where this scaling was come from. These are very empirical studies, lots of curve fitting engineering. And that creates some problems. So problem one, I mean, the cost of training these models get like very expensive on the order of hundreds of millions of dollars, right? Only very few companies have these kinds of resources. So this creates problems about like, monopoly. And of course, by training bigger and bigger models means you're going to use more and more electricity. So people estimate that 3% of global electricity consumption will be basically data processing related in a few years. What I want to emphasize here or maybe convey the message is that this is actually a problem that theorists, I'm an applied math professor, so mathematicians can help by basically figuring out where these power exponents come from and can we improve them and get efficiency. So it's a good mathematical problem to attack with real life impact here. Okay, but of course, to be able to do that, first, we need to understand what determines these scaling exponents, where these numbers come from. And what I want to tell you is basically, we don't have an answer to that, but there are some theories around. So I'm just going to give you a little background of what people think where these things come from, in the order of, some order, starting from simple ideas to more complex ideas. So here are two ideas. Okay, so let's again look at this scaling exponents. So this number is 0.34, this number is 0.28. Okay. So the first, when I look at this, my physicist mind asks, well, the first question I would ask is, why are these exponents not 1? Okay, so the reason for that would be the following, right? So, these models are trained at a large something limit, a large number of parameters or a large number of data, right? So if you're familiar with statistical mechanics or statistical central limit theorem type ideas, right? If you're taking some size to infinity and you're approaching the limiting object, a statistical object, right? So there are going to be some fluctuations around that. And you expect those fluctuations to be of order 1 over whatever the scaling parameter is. Right? So a very natural guess would have been that this should be like 1 over n or 1 over t. But these numbers are not 1 over n or 1 over t. In fact, I mean, we've done a careful analysis of this in an earlier paper and showed that, if you are really taking a model and really fixing a data set size and really taking the width to infinity or some parameters to infinity around the limiting object, you would exactly see these kinds of fluctuations. But that's not what you see, what people see in experiments. Okay, so how do we explain these non-trivial power laws? By non-trivial, I mean this guy is not wrong. So here's another observation. So these are experiments that I've done, we've done. So here, what we're doing is basically plotting a test loss. So again, some loss of a model as a function of training. Okay, and what we are doing is basically scaling it up, growing it up bigger and bigger. The particular architectural thing that we're growing here is the number of heads. So it's an attention module. If you don't know that, what that means is that's unimportant, but there's some, unit of some architectural unit here, which are attention heads that we are making bigger and bigger and bigger. Okay, so as the models are getting bigger and bigger and bigger, basically the loss gets better and better and better. So I'm going to do the following plot. I'm going to look at this plot early in training and late in training, and then basically plot them as a function of heads. Okay, so that's what this plot is. So early in training, what you're seeing is basically a power law that's more like 1 over h. This is exactly the thing I told you. You're approaching a limiting object like a central limit theorem, and that's exactly what you will see. But as you go later in training, you come up with a power law dependence that's not 1 over h, that's something else. So something else is happening over here that's not explainable by approaching the limits. It turns out it can be explainable, but not in a very trivial way. Okay, so these are some observations, empirical observations about how this behaves. Okay, good. So let's think about, so what are the ideas that exist in literature about explaining this, starting from some easy to more complicated ideas. So the first idea came from Kaplan, Sharma and Kaplan of the first paper I've also mentioned. So they had an idea about explaining, this whole thing by the following idea. So let's think of data living in a manifold of intrinsic dimension D. Right? So not the ambient dimension, but intrinsic dimension. So they're thinking of basically a machine learning model as basically sort of approximating a Lipschitz function, this function being the input-output map that you're trying to learn, using piecewise linear regions. So divide the whole manifold into small hypercubes, okay? And you want to have like basically a linear regression in each of these hypercubes. And then there's some kind of this one parameter for every hypercube. Okay? So if you just turn all of this math into some back of the envelope calculation, you can argue yourself that the loss should basically fall like 1 over n being number of parameters to the power 4 divided by d being the ambient dimension of this data set. So this is all about like how data is embedded. It doesn't actually talk much about the function itself is complicated or not. I'm going to be quick about this. I can tell more details, but that's one idea. There's a later idea from Hutter. So it's a more, I guess, a global picture. So just here's how he argues how laws might arise. So suppose you need to learn a certain number of features to be able to solve the classification task. Each data point exhibits one particular feature. And if you want a correct classification, that requires that a feature K appears in the training set. Okay, so that's the idea. And then, so you can basically argue that if the probability of a particular feature K appearing in a data set goes like a power law, okay, then this is basically the probability of that particular datum exhibiting one feature appearing in the data set. P is the data set size. You can convert this basically into, so again, back of the envelope calculation, and show that basically you can get like some kind of power law scaling with data set size of this. So this is a simple idea. I don't know how to test this idea, but that's one idea. There's a third idea, which is coming from Matthew Wiart and students and collaborators. So what they were saying is basically data has hierarchical structure. Okay? And this hierarchical structure can help escape the curse of dimensionality and give rise to power laws. There's a lot of math, if I were to explain this, that I won't go into. And there's a fourth idea, which is the quantization model by a bunch of folks over here, which is sort of like the Hutter idea, but here's its 5 sort of assumptions, okay? And I'll just read them to you. So instead of features, they're thinking about basically an LLM making a prediction about the next task. And they assume that prediction tasks decompose into a quanta of skills. So you need to have a certain number of skills to make the prediction. And some quanta are more useful for reducing loss than others. Right? So, you know, probably addition is a more useful skill for real world than, I don't know, trigonometry, for example. Right? The frequencies at which the quanta are used for prediction follow a power law. A network with n parameters can learn n over c quanta. C is for capacity, so there's some bottleneck over here. And power examples utilizing quantum K are needed in the training set for quantum K. So you need to be able to learn the skills, you need a certain number of examples of them. So if you put all of these numbers, all of these assumptions into, again, a back of the envelope calculation, you can come up with basically a power law dependence of test loss. And that dependence is going to be a function of basically this power law and a tau and so on. So I'm not going to display what it is, but these are just the ideas that are out there. Okay. So these are very high level ideas. Right? So is there like a sort of a more mathematical idea out there? So there is a powerful toy model, and this toy model goes under the name random feature model. So the model is particularly a very simple model of this. So X is again a data point. Phi here is basically a high dimensional vector. So what makes this a random feature model is that this is a random function. We can compose it in different ways, so we don't have to go into the details. And then on top is basically a set of parameters that learns a W dot phi. Is your model's prediction. Okay. So it turns out by studying this model, and again, many people, including myself, have written tons of papers about this particular model. So if you put one particular ingredient to this model, and that particular ingredient is this idea, that the data itself has power laws in them. And this is true for most natural data. So if you just take some images, do a PCA on them and then order the eigenvalues, you will see that, like, you know, the eigenvalues fall like a power law. This is true for almost any natural data set over there. So if you plug that in, and then you can do your favorite mathematical sort of pool and apply and try to solve the mathematical problem that comes out of this, you can come up with equations that looks like this. So what does this? What is this showing you? The loss is a function of number of training time, number of parameters. If you're doing SGD batch size, gamma here is something I'm not going to go into. Okay, can be described by basically a collection of different terms, and their asymptotic behavior is given by these particular functions over here. For example, it might be a power law dependence on the number of training steps you take. It might be a power law dependence on the model's size, and being here number of the dimensions here. If you're doing SGD, number of batches, and so on and so forth. And depending on, you know, which of these numbers are bigger, you know, some of these guys will be negligible, and the dominant one will be the one which is dominating this particular loss, and you will see a power law in that particular resource. Okay, so again, there's a lot of theory on this. So this is actually a pretty powerful toy model. Okay, just to give you an idea of what kind of things it can explain. All right, so it can explain the following. So just to give you maybe one more idea about like where these kinds of things arise from. So here is the idea. Now, I said that, you know, you have to assume that data is power law correlated. So the eigenvalues here are some power laws. So that's that assumption. The eigenvalues here are given by some rank order. The eigenvalues are given by k to some power minus b. And also, there's another technical assumption about what these weights should be. So, you know, they also could be, there's an underlying data set, and that underlying data set is a particular class assumption, classification condition, and that can be also described by, you know, the weights can be described by a power law. So if you do this math again, so here's some intuitive way to see what's happening. So I'll just show you like 3 examples here. Suppose what we've done is given this P in this particular slide stands for number of data points or data, N stands for number of parameters. If you made this model extremely big and gave it a lot of data, right? So, and I'm thinking of training to greater percent. Okay. And obviously, the limiting resource is number of training steps, right? Because if I haven't trained anything, I haven't learned anything. It must be the limiting behavior. So the leading behavior of the loss is going to be a power of number of training steps, and then these guys are going to be basically following from these two instances. We can look at the model bottleneck, for example. If I gave the model a lot of data and trained it too long, but if my model is not powerful enough, that would be a limiting resource. So the leading sort of contribution to the loss will be defined by a model bottleneck, some power of n, again, the power defined by these guys. And the reason I'm displaying this is actually there's a very nice interpretation of why this happens. So if you were to, again, do this calculation, at some point when you're taking these limits, what you realize is here's what happens. So the loss can be written as basically a sum of the power in particular eigenmodes of the data. Okay, so that's given by this subject over here. But the point is there's a cutoff sort of eigenvalue. Eigenvalues smaller than this are all learned in a sense. They don't contribute to loss. And the tail sum is basically all not learned. Okay, so there's a particular critical eigenvalue here. And a particular eigenvalue is given by exactly, if you're in a data bottleneck regime, the number of data that you have, meaning that as you keep adding more and more data, you learn more and more eigenvalues of the data. If your model bottleneck, that particular cutoff is given by a number of parameters, meaning that if you're adding more parameters to your model, you can resolve more and more data eigenmodes, and therefore basically get this kind of scale law. And time bottleneck is a similar. So there's a conversion factor here. It's not exactly t over 1 over b because it's a technical point, but if you're doing gradient descent, there's a time constant that gets associated with every dimension, and that gets that particular thing is the eigenvalue. So we're going to go this. Okay, so what can this explain? So here's a typical curve that we can look into. So this particular one is coming from this random feature model, but it's basically shows the same behavior that you would see in a real training learning curve in a big model as well. Again, I'm plotting loss versus time, and then early in training. So what's happening here? These are different models of different size. I guess something's happening. Models of different size. So as you're training more and more, basically models start saturating. Yeah. So larger models basically fall more and then start saturating later. And why is that happening? Because early in training you're limited by training time, so everything follows the training law, power law. But later in training, now you have trained a lot, but now the model's size becomes the dominant, the bottlenecking factor. So basically, we transition to a different scaling regime. Okay, and so this is exactly what you would see if you were to plot these losses as a function of early time model convergence, right? So as a function of model size at early training time versus late time, you will basically see these different power laws. Early in training, because I'm bottlenecked by time, basically my scaling exponent with respect to parameters is 1 over n, but late time basically it switches with other particular regime. Okay, so let's have an idea out there, and this explains basically some basic factors about basic facts about how scaling behavior happens, especially this fact about being dominated, so being bottlenecked by certain resources, whether that's data or parameters or training time. But does that explain what happens in real life? Okay, so here is again, so this is what I want to show you. So what you can do is basically plot test loss as a function of training time for these two different conditions. So this is a convolutional neural network trained on some MNIST variant, and this is a CFAR variant. And what you see is basically these solid curves are neural network training, and these dashed lines are basically what this theory would predict. Okay, and in this case, you seem to get the power exponent correctly. In this case, you seem to get the power exponent correct. So maybe I should say the different lines here correspond to different hyperparameter choices for this network. So think of these as some different hyperparameters. So in this case, basically, you see that this theory explains something, but it misses something else. So there's a factor here, there's a training regime here how these random feature models don't basically capture. Okay, so long story short, these are all the existing ideas about neural feature power laws, neural scaling laws out there, and this is their predictive power. So it does capture, it seems to capture the scaling behavior in simple data sets, but when data sets get more complex, basically, then you seem to be missing something. But that's not the only way they fail. I mean, even though this is my work, right? So they also, I mean, do not capture, if you're thinking about large language models, essentially that's aspects of language data that are sequential that none of these models are actually capturing. So that's one problem. We need some more advanced solvable toy models that capture and elucidate essential aspects of sequential data. So that's one idea. And further, there's this other idea of emergence that basically these models don't show. Okay, so let's discuss about this. So this is a paper that came out like a few months ago. So here's what they're plotting. So these scaling laws, I mean, show predictable relationships. But what is predictable is basically test loss or the performance on the next token prediction task. But you can take a large language model and ask it other questions, for example, to solve a math problem or any other problem you might, and see, for example, if they end up having predictable relationships with scale. So what this is showing is exactly things like this. So on the y-axis is the model's performance on a task, that task being, for example, some elementary math question and answering or logical deduction or CS algorithms. And on the x-axis is cross entropy, basically it's performance on next token prediction. Some tasks get better as the models get basic. So cross entropy is decreasing this way. So this is better next token prediction. So some models get better at their accuracy on, for example, math, whatever this AS and easy task is, as models get better language models. There are other tasks where basically the models get worse at solving them. So this one's the math task. And this one is an interesting one. This is the one I'm going to talk more about, right? Some tasks show this emergent kind of behavior, by which I mean the following, the model's performance below some scale is basically almost zero. And suddenly there's a big jump and the model behaves, good at it. Now, obviously, and there's a taxonomy of basically, or like a pie chart of, the particular kinds of trends in these downstream tasks that these authors have seen. But what I want to emphasize is this emergent behavior, in particular because it has a lot of important implications for AI safety. Why? Suppose, this breakthrough itself, or this emergent behavior was the model's, let's say, tendency to kill human race or something like that. So if it showed no tendency here, and you assume that it's going to stay that way, and suddenly there's an emergent behavior, that's obviously not nice. That's something that you don't want to be in a situation like this. So therefore, emergency is an important subject. So this is also another sort of area where we need a good solvable model. Okay, so for today's talk, what I'll do is basically an update to these toy models, in which basically I will be talking about the theory of scaling and emergence in something called in-context learning. There should be another in here. And what do I mean by in-context learning? So this is an emergent behavior that an LLM shows. Okay? It is the ability to learn and execute tasks based only on examples seen in inputs without needing explicit training. So this is sometimes contrasted with in-weight learning. In-weight learning would mean that to learn a new thing, I have to update my weights. Okay? This is what we're talking about. In-context learning means that I will keep my weights or parameters the same. I'll just give the instructions at test time by writing, for example, on a prompt. Okay? And that the model is going to learn directly from that. So here's a typical example. So I'm assuming that this example is something that the model has never seen before. Okay. So this is what I'm going to give it, some input-output examples. Input is, some dates. Output is basically this. You see there's some clear rule here. I'm going to change the month and the day, and then I'll put the year at the end and change these dashes with exclamation marks, so on and so forth. Right? That's the rule. And then as input, I'm going to give this, and I'll expect the model to output basically this. Right? So the idea is that the model is going to learn this in context, context being that basically I'm writing it the prompt. It's not to understand the rule. Okay. So large language models are able to do this. You can try, and they can do this. And yeah, and also people have sort of argued that this is an important sort of property because it enables language models to perform new specialized tasks without retraining, which is arguably a key reason for the general purpose ability, right? So you can retrain them this way without updating their needs. And this is a paper showing basically this particular property, right? So the emergent property. So this is a paper that talks a lot about other tasks, but Wei et al. But one of the things it does is an in-context learning task, and then and the thing it was arguing was basically 50% here would be the way they implemented this would be a chance level, and basically there's a jump at a particular scale, but it's an emergent property. I'll talk more about this. Okay, good. So you can ask questions about, what algorithms do transformers implement for in-context learning? How many pre-training examples required for it to emerge? How many examples should I be giving for it to learn in context? You can ask tons of questions, right? How do different optimizer and hyperparameter choices affect ICL performance? All that kind of thing. So, and turns out you can answer all of these questions in a particular simple solvable model, and this is described in this paper, which I'm going to talk about now. Okay, so the task we're going to talk about is basically ICL in-context learning for linear regression by an attention module, a special one, a linear attention module, which I'm going to describe. And this is by no means something we sort of invented ourselves. There's tons of other people who have studied this particular problem. And also lately, you have also, Zafer Doğan, sorry about this, people in this room that has studied this model as well. Okay, so what is that? How am I going to set this up? In the following way, so let's think about the Bayesian way of thinking about this. So given a pair of XY pairs, so X is the example, Y is the output, right? What I want to give is basically another XL plus one, L being the context length here, and I want to predict the corresponding Y. Okay. So the way I would sort of formalize this is the following. Suppose there's a collection of joint probability distributions over XY pairs. Okay. So for each input sequence, you would basically sample one sort of distribution or measure from this collection of distributions and generate this sequence from that particular measure. And then basically ask the model to figure out what that is. Okay. So during the pre-training, what the model should be doing, it should be learning the prior distribution over basically all these measures. So that's the way I'm going to sort of formalize this. Okay, so and I'm going to even simplify this further. Okay, so let's commit to a particular way of doing this. So I'll assume that the relationship between X and Y here is basically just linear. Okay, so in my notation here, the brackets are just doctrinal X. I'll just also add some noise to make this simple as well. So the model just sees a bunch of XY pairs. Okay, so let's make some statistical assumptions here. So let's sample these X's from some Gaussian distribution of they're going to be dimension D, add some noise, and and for each sequence, basically, I'm going to choose W again from a Gaussian distribution. However, basically, this particular vector itself, even though it will be the same vector for each context or sequence, will be a different vector for each different context. So that will be the idea of in-context learning here. The model has to figure out what this W is context to context. Okay, good. So this is the idea. So how am I going to train this model? So I have to come up with a training set. So it's a similar idea. I'll just give it the same task, right? So now I've introduced a mu index here, mu being the basically the training data set contains n input sequences, and I'm going to label these input sequences or contexts with mu. So here is one twist that's important to understand. For training, I'm going to introduce this notion of task diversity. Basically, I'll commit to choosing W's to be one of k things. Okay. So why is this important? So let's think about this. So if k was equal to 1, meaning in all different sequences, the model has just seen the same W, right? It would have seen a very narrow set of tasks. Therefore, you wouldn't expect it to learn to do in-context learning, because it will always assume that it's the same W in training. Therefore, in test time, that's probably the usual thing to do. If I was basically choosing a random different W for each input sequence, that would be a very diverse set of tasks. And the model probably would expect that in each example, I'm looking for a different W, right? So to be able to control for this, I'm going to introduce a set of K, basically, meaning so N and K are different, meaning N is bigger than K. What that means is basically there will be some input sequences with repeated Ws, but basically different X and Y. That's the idea. For the meal sequence, sample task vector W mu, uniform net random from this task vector set. Okay. All right, so let me first explain the main phenomenon I want to address. So then I'm going to introduce you some experiments that somebody else did about this thing. So, and to be able to explain this experiment, I need to introduce two Bayesian benchmarks. What do I mean by this? So I'm going to compare the transformers prediction to something else. What are those two things? So one is basically a Bayesian predictor, which I'll call discrete MMSE predictor. So the idea here is the following. This predictor will assume that this W itself is coming from one of the K things I've seen in the training set. Okay, so that's the discrete MMSE Bayesian estimator. And the second estimator, which I'll call within context Bayesian estimator, will be a ridge regression estimator. The Bayesian version of this says the prior is that this W is just coming from a Gaussian. Okay, so I'll assume that this W is not one of the K things I've seen in my training set, but in a Gaussian. So this will be a Bayesian ridge estimator. Okay, so this is more like in-context learning. So if you've been following what I'm saying, okay, this should make sense to you that this is more like an in-context estimator. Like it doesn't assume anything about my training set. And this is like a memorizing solution. It has memorized these K task vectors. That's basically trying to see, which of the K task vectors it is modeling. So here's an experiment. Here's the experiment. So it's an experiment from Surya Ganguly's lab at Stanford. So here's what you could make interesting finding is. So what are we looking at here? So this is the model's prediction performance in solving this task. On the x-axis is basically the K number here, number of pre-training tasks. K is the number of Ws in the training set. Okay, so we're looking at three curves here. The blue one is the estimation. So the task is, again, in context learning. During test time, I give it a different W at every context or sequence. But the blue one is the performance of the ridge estimator. So that is the Bayes optimum estimator. So it gives a very good performance. The green one is the discrete MMSE estimator. So this is the memorizing solution. In the beginning, it starts high. And as you go increase the number of pre-training tasks, it starts behaving better and better and better. Okay. And as you can understand this, because, as the number of pre-training tasks increase, basically the coverage of Ws, KWs is very good. So it's almost approaching ridge estimator. And this is what the transformer does. Early in training, it behaves like a DMMSE estimator. And late in training, it behaves like a ridge estimator. So it's transitioning from memorizing the K tasks to truly learning an in-context learning solution. So that's the transition that we make. So the question is, of course, why does this happen? And what's special about this particular number? Why does it happen this year? The questions about this? All right, so we can explain this transition in a single layer linear attention model. So what do I mean by this? So I'm going to build this up. And I'm again going to run out of time, but it's all right. So we'll try to get the basics to you. Okay, so what I'm going to do is basically take this data set and give it to an attention module. I'll describe what that means. So first, I have to organize this data. I'm going to embed this data in a particular way. I'll go pick X's and Y's, in this particular format in a matrix form. And then so this 0 is basically my notation for make a prediction here. Okay. So linear attention is this exactly this equation here. So K, Q, and V are the parameters, value, key, and query matrices of the attention. Z is the inputs. So usually you would have a softmax operation here. I'm going to remove this. I call this linear attention not because it's a linear function of C for a different reason, but it's obviously a nonlinear function of C. Okay. And then, of course, what comes out of this is the matrix that was the same size as Z. So I'm going to commit to this lower right corner as my prediction. How I'm going to set this up. Okay. So before doing any math, but just by simple algebra, we can see a lot of things here. So let's just work through this. How can linear attention solve this task? So this is, I just took this algebra and wrote it out. And this is how it looks like. So it turns out, so this M here and V here are basically keeping all my parameters. And X's and Y's are here, what I've given in context examples. And this X is the prediction that I want to make, the X with respect that I want to make. So what can I see from here? And it looks like a complicated expression. So there's a particular term here that's very informative. So let's look into this. Okay. So there's a bunch of terms, but this is the first term. Okay, so let's look at what's happening here. Again, these are a bunch of parameters. And here is basically the examples that I've given. And you're seeing basically a simple sum here of X times Y. So it's like a correlation function here. That's what's happening. You can immediately see how the model could solve this. Notice that Y is W dot X. And so this sum is basically roughly an estimate of XX transpose average, so covariance of X times W, right? So if by some magic, the model had learned in its parameters to invert its covariance matrix, right? So if that's what these parameters were, then you would just get a W here, and by W times X, you would be able to solve the problem. Right? So that's how you would be able to solve the problem. Very simply. Okay, but how would this work? So let's think about the setting here. We want to work in a high dimensional setting. X is a high dimensions. To be able to get a good covariance estimate, you want to have a sum here L that's of size D, right? Because if L is smaller than D, much smaller than D, you don't get a good covariance estimate. If L is much larger than D, you get a perfect estimate. So this is the random matrix reasonable limit. You need to be able to estimate parameters. How many parameters? Well, you need to be able to estimate about the covariance matrix that has about D squared elements, right? Okay. So that means the number of examples that you provide to the network should go like roughly D squared. So task complexity, how many Ks do you need? So it's not obvious from here, but you can show that it also has to scale with D. So before doing any math, you can just by looking at this expression, you can tell a lot about how this should be worked. Okay. So this is intuition. Okay, so what we're going to do is basically to proceed, we'll simplify this attention predictor. This is very complicated. So we're going to basically ignore those two things. And we're ignoring those two things for a good reason. And I can tell you why. Let me tell you why. Because this guy is basically projecting X to a particular dimension, both of them. And the problem is basically isotropic. So there shouldn't be any particular important direction. So you would expect that these basically terms are not doing anything special, which turns out to be roughly true. So we can just focus on this. And then, so after committing to these two terms, what you can just observe is basically this boils down to a matrix trace between a parameter matrix and some data matrix. This data matrix is a random matrix. It has like interesting correlations. It's not like a Gaussian matrix or something. It's pretty complicated matrix, but roughly that's what the prediction is doing. Okay. What that means is, so committing to training this gamma aggregate parameters, okay, I can come up with a pre-training term, which is basically predict the next token by this, okay, which is a linear regression problem. And I can solve this analytically, right? And then do some random matrix theory with this. Because the solution itself is a random matrix involving some vectorized tensors of random vectors. And then I'm not going to the math details of this, but we can use RMQ analysis algorithm. Okay, so let me skip this, but the idea is basically we can analyze this in an asymptotic limit where I take D context length, number of context sequences in the pre-training data set, and task diversity going to infinity, such that these ratios are fixed. The idea that, and I sort of argued why you should be expecting these kinds of ratios over here. Context length should go like D, K should go like D, and the examples should go like D squared. Under these assumptions, basically, we can exactly solve this model and exactly answer all these questions about sample complexity, context length, and test sample complexity. Long story short, there is basically a mathematical theorem that it tells you exactly the in-context learning generalization error, okay, which is complicated. But let me give you basically 2 or 3 examples of what you can extract from these equations. So one thing that you can extract, for example, is basically you would extract some. You can see that this model also shows a property called double descent. What that means is basically, as you're adding more and more training examples, the in-context learning starts falling, then gets basically some peak and falls again. There's some non-monotonic behavior. And the scale at which this happens is basically where n is number of training examples about d squared. So that comes from this model. Let's skip this. You can see things like non-monotonic dependence on context length. Basically, more data in context doesn't mean that it's always good. It's actually non-trivial result. I still don't understand why this works. But more importantly, so let's come back to this picture and this particular fall over here. This model shows exactly the same behavior. So let's look at the plot here. I'm plotting again in context learning as a function of task complexity. And then these are showing our theoretical plots over here. And then alpha here refers to context length, how much data that you provide. And then you see that the models are, so this is the MMSE predictor. This is the one that's memorizing. And this is the rich predictor in this case. And the models are behaving like MMSE before and false to rich predictor later on. The scale at which this happens is exactly at k is equal to 1. So meaning that the number of task vectors is equal to the number of data dimensions. So that's exactly what you can get out of this theory. And not just that, we can, so this was all for this toy model. Now we can test these ideas in real transformers. So for example, let's look at this curve over here. This is basically 2 blocks of softmax attention and 1 layer MLP. So it doesn't have any of these linear assumptions or single layer assumptions we've done. Okay. So I'm plotting its ICL performance as a function of number of training points I've provided. But basically, I rescale the, so these are all models, same size, but trained with different dataset vectors, X vectors of different sizes. These 20, 40, and 80. And if you plot the right scale over here, you see that these models almost all collapse onto each other, with basically the peak happening around tau equal to 3, not 1, but pretty good, sort of good for theory, I would say, that we get this scale relationship right. It also shows that we can also repeat these experiments where you get like the fall of the predictor from being memorizing to a generalizing solution. Okay, so long story short, and I think actually I have 5 minutes. So let me say just a few more words and finish. So this was the base model. It basically captures a lot of interesting things. So what you can do is generalize this particular toy model in different ways. For example, we've committed to this idea that during test time and training time, the task vectors were coming from the identical distributions. So we can also relax that assumption. So basically, and then there's some mismatch in tasks. And then you can show that something, you can do some math. And what you can show that math boils down to is the following. The total in-context learning error can be written as an expression that has these 2 terms, something that depends on the training task covariance times the trace of the test time covariance. So not times, but a function of it. And there's another term here that takes the full covariance itself. So this is very weakly sort of dependent on test, and it depends on the test. Okay. So basically, it's interesting because this is basically a metric of how much the test time task is aligned to all the tasks that you see, right? If you're interested in basically the kinds of matrices that you need to look at, so when you're driving this expression, you need to look at calculate spectrum and other statistics of a bunch of random matrices, and they're all shown here. Don't need to go into this, but so here's basically what comes out of this. I'm not going to show you the exact theory. Exact theory is exact, so we can solve it and prove that, you know, its assumptions are correct, the math is correct. But this is basically the test of this theory on something with just on two-layer transform with softmax attention. So what we are plotting here is basically on the y-axis is the in-context learning error again. On what? On basically where the training and test task covariances were different, okay? And on the x-axis is we're plotting how aligned they were. And on the y-axis is the performance of the model itself. And you're seeing that there's a perfect correlation with our theory-derived measure and predicts basically how good or bad compared to other sort of past test covariances that this model could make. So that's one thing you could do. And the final thing I'll mention is basically what happens if we stack L attention layers, not just one layer. Now, I've given you some intuition that if X covariance was fixed, the model could memorize that by its parameters and solve all of this in one layer, right? But if it's not fixed, meaning that the X itself has a context-dependent covariance, then this is not a possibility anymore. And then what happens is basically depth becomes important. Then you need more expressivity in your models. And we've worked this out, so I'll just give you one gist of it, glimpse into its results. And this is going to tie back to basically the idea of power laws from the beginning. So if you assume that basically, you know, the eigenvalues of X is all fall like a power law, its W's have some power laws in them, you can show that the loss itself, this is in population loss limits, so I'm not going into the details of this, but can be described by a functional form like this that has power law dependence and training time width dependent and context length. So these are sort of expected. So, but this particular one is like was something new to me, right? So you can get some also power law dependence on context length as well, and length as well. But here's another interesting finding. So I mentioned to you this chinchilla learning rule, chinchilla scaling paradigm, where basically depth, the model parameters were supposed to scale with data set size. But you know, when you're scaling model parameters, you can scale width or depth or other architectural parameters. Parameters are not the same. I think the depth is not the same as the width. So people are doing empirically proportional scaling, meaning when I'm scaling width, I have to multiply depth by 2 as well. Is that optimal? So in this model, you can actually work this out and show that, like, you know, when you're adding more depth, that should go like power of width, and the power scaling exponent also optimally, optimal scaling exponent should come from the data itself. Okay, this is just to show you that what you can do with this model. All right, so with that, I've presented a solvable model that includes a simplified attention block, which is still nonlinear inputs. The model shows emergence and shows differential scaling behavior with respect to depth, width, context length, and training behavior. But I mean, basically, and for people looking into problems to work on, this is just the beginning, right? This is getting closer to the complexity of, you know, real LLMs over here. But we do need more advanced solvable toy models for making progress in basic understanding where these problems come from. Okay, with that, I want to acknowledge my students and collaborators and the people who have contributed to this work. And thank you for your time.